We are pleased and delighted to have Professor Takaaki Kajita with us for this IOP Golden Jubilee Colloquium. First of all, we are very thankful to you, sir, for accepting our request and giving us your time. So, first of all, I would like to request our director, Professor Karunakar Nanda, to give his inaugural address.
Okay.
The stage is yours, sir.
Okay, so especially as we are at different time zones. So good morning to all actually who are participating from India. Good afternoon, who is participating from Japan. And probably good evening who are participating from US. Actually, those who don't know about our institute, the Institute of Physics Bhubaneswar, it was established in 1972. But the academic program started in the year 1974. So keeping that academic program in mind, actually we have started celebrating from 23 September till this coming September 24, again the golden jubilee year. And during this 1 year time, actually we are organizing different conferences, outreach programs, colloquiums, seminars, and all. And we have each month we are conducting few events. And we are planning to organize one colloquium, one seminar every month. And Professor, especially Biju Sekhar, is taking care of these things. So I must thank him actually to come up with a plan and doing it actually in a holistic way. And especially, our colleagues actually at IOP, they are engaged in various branches of physics like high energy, both experimental theoretical, condensed matter, high energy, condensed matter experiment and theory, nuclear physics also. And especially I talk about Bhubaneswar. This is the capital of Odisha. And if you look at the literal meaning of Bhubaneswar, Bhuban plus Ishwar, so it's basically Lord of the universe. So where we have Lingaraj temple, where Lord Shiva is being worshipped. And, I welcome all of you. If you are getting a chance to come to Bhubaneswar, I would invite all of you who are coming to Bhubaneswar to come to the IOP and see our facilities. And we can interact with our colleagues also. And today, actually, we have Professor Takaaki Kajita. We are happy and delighted to have him here, as our colloquium speaker. Especially he's from Institute of Cosmic Ray Research, ICRR, University of Tokyo, Japan. We are grateful to him for accepting our request to deliver the Golden Jubilee Colloquium of our institute, in spite of his busy schedules. I have few information about him to share. Professor Kajita has made fundamental and path-breaking contributions in the field of high energy physics, with a special emphasis on the properties of cosmic rays and neutrinos. In 2015, he was awarded the Nobel Prize in Physics for the discovery of neutrino favor oscillation, a phenomenon which confirms that neutrinos are massive particles. He is currently the president of Science Council of Japan. He is the distinguished professor at the University of Tokyo. Professor Takaaki Kajita is currently the principal investigator of another ICRR project located at the Kamioka Observatory. So apart from the Nobel Prize in 2015, he was awarded with other prizes also, like Bruno Rossi Prize in 1989, Panofsky Prize in 2002, Breakthrough Prize in Fundamental Physics in 2016, and many more. And especially Professor Kajita has been playing an important role for science outreach for the last couple of decades. He has been also helping the Indian-based Neutrino Observatory project, which is one of the flagship mega science projects of our country, in many ways, including science outreach. And IOP has a strong visibility in the field of neutrino science inside India and abroad. Our faculties are involved in various cutting-edge research related to neutrinos, starting from neutrino oscillations, neutrino mass models, role of neutrinos in colliders, and many more fundamental issues. IOP as I understand, is deeply involved in the detector and physics simulation studies related to INO project. And I am quite hopeful that in coming days, there will be opportunity to have scientific collaborations between India and Japan. And I can assure Professor Kajita-san that IOP faculty will play a significant role in such activities. So I thank especially Professor Sanjeev Agarwal and Professor B.R. Sekhar, and of course, Professor Dige for, finding some time, especially to, introduce the speaker in a more detailed way. So, and especially Sanjeev Agarwal and Professor B.R. Sekhar for arranging the colloquium. So I'm looking forward to your talk, sir. Thank you.
Thank you, Professor Nanda, for your inaugural address. And now I would like to request Professor Amol Dighe to formally introduce our speaker. He is one of the renowned neutrino physicists of our country and playing an important role to promote neutrino science in many ways and guiding us for over the last 2 decades. So I would like to request Professor Dighe to introduce our speaker.
Thank you, Sanjeev, and thank you, Professor Nanda. It's a matter of honor and pleasure to be able to introduce Professor Takaaki Kajita, whom I know in the scientific capacity for many, many years. I'm sure that most of us do not need any introduction to him as such, but for the benefit of some, maybe I will just tell a few things about him. Of course, he received his Nobel Prize in 2015 for discovering that neutrinos oscillate among different flavors and therefore they have mass. This is one of the, in fact, the first signal of physics beyond the standard model of new physics. As we know, the standard model is the best known theory that we have of how fundamental particles interact. It has been well established, and people are trying to find signals beyond the standard model. Till now, in the quark sector, we have not succeeded. However, in the last century, there were these two long-standing puzzles which almost took decades to solve. One of them was the solar neutrino problem, other was the atmospheric neutrino problem. And the major contribution of Professor Kajita is actually in solving the atmospheric neutrino problem by showing that neutrinos indeed oscillate. A couple of small things I would like to mention. One is that he, in some sense, is responsible for my coming to neutrino physics. My PhD was not in neutrino physics. I was actually working in the quark sector. And I was working as a postdoc in ICTP, where I refused to work in neutrinos unless the proof of neutrinos having mass came up. During 1998, there was Neutrino 98 conference in Japan, where Professor Kajita gave a talk. I did not go for the conference. I was sitting back in my office room. The next week, my postdoc supervisor, Alexis Smirnov, came and showed me the famous 6.2 sigma transparency of Kajita-san and basically said, here is the transparency. Now we know that neutrinos have mass. Now you have to start working in neutrinos. So he is in some sense responsible for my first foray to neutrinos, and I really thank him for that personally. Even after that, I think one of the first comprehensive way of learning about the super Kamiokande experiment was actually his thesis, which is written in very detailed. And that was one thing that helped also make my concepts in neutrinos very, very clear. As we know, he is, of course, a very well-known physicist, a Nobel Laureate. He's also a very good speaker and explains things extremely clearly. Just like you, I'm also looking forward for his talk. And maybe now I will welcome Professor Kajita to deliver his lecture. Please.
Thank you, Amol, for introducing our speaker. So without wasting any time further, I would like to sincerely request Kajita-san, if you can kindly share your slides and take us into the world of neutrino oscillation experiments.
Okay, well, thank you very much. Well, thank you very much for the kind introduction. Also, well, I would like to congratulate the Institute of Physics for the Golden Jubilee. And in fact, it is an honor to speak in this occasion on neutrino oscillation experiments. Okay, today I want to outline the neutrino oscillation experiments. Okay, this is the outline of this talk. First, as an introduction, I'd like to review the neutrino problems. Then I want to move on to neutrino oscillation studies. The first is nu mu to nu tau oscillations. The second channel is the nu e, that is electron neutrino to mu neutrino plus tau neutrino oscillation. And since there are 3 neutrino flavors, there should be the third oscillation channel. So I want to discuss the third oscillation channel. So far, we understood the basic structure of neutrino oscillations, but there are still unknowns in neutrino oscillations. Therefore, before finishing this talk, I want to briefly discuss the future prospect. The first topic is the mass ordering. The second topic is CP violation, and I'll summarize this talk. Okay, neutrino problems. First, I want to discuss solar neutrinos. As you know, the sun generates energy by nuclear fusion processes. Neutrinos are created by these processes. Therefore, the observation of solar neutrinos is very important to understand the energy generation mechanism in the sun. In the middle of this slide, I show the calculated energy spectrum of solar neutrinos. So you find sub-MeV to MeV neutrinos are created by various nuclear fusion processes. Therefore, the solar neutrino experiments should observe these neutrinos. In fact, the pioneering Homestake experiment observed solar neutrinos for the first time slightly more than 50 years ago. That was great. However, there was a problem. The observed event rate was only about 1/3 of the prediction. Well, people were confused. There were several discussions. For example, some people wonder if the experiment is properly done, or some people wondered if the solar neutrino model calculation can be accurate enough. In any case, because of this problem, several other experiments tried to observe solar neutrinos. In the 1980s, the Kamiokande experiment observed solar neutrinos, but also this experiment observed a deficit. Then in the 90s, gallium experiments, one is the SAGE experiment in Soviet Union or at present Russia. Another experiment was the Galax GNO experiment in Europe. These experiments can observe low energy solar neutrinos, and indeed they observed, but again the event rate was much lower than expected. So these solar neutrino experiments observed the deficit of solar neutrinos. So This was the solar neutrino problem. Now, I'd like to change the topic to atmospheric neutrinos. As you may know, cosmic ray particles come into the atmosphere of the Earth. These particles interact with air nucleus, typically producing pions. And of course, pions are unstable, they therefore decay to other particles. And during these decays, neutrinos are created. And these neutrinos are observed in underground experiments. Now, in the 1980s, several proton decay experiments started. Unfortunately, these experiments didn't observe proton decay, but instead, these experiments observed many atmospheric neutrino events. And because atmospheric neutrinos were the most serious background to the search for proton decays, therefore it was necessary to understand atmospheric neutrino interactions. And during these studies, a significant deficit of mu-neutrino events was observed. And in fact, the Kamiokande experiment and the IMB experiment observed deficit of mu-neutrinos. As you see in this plot, the deficit was indeed a significant. Now, I'd like to move on to the neutrino oscillation studies, nu mu to nu tau. First of all, let me introduce the importance of neutrino oscillation experiments. In the standard model of particle physics, neutrinos are assumed to be massless. However, of course, physicists have been asking, neutrinos really have no mass. Also, it was generally believed that if neutrinos have very small mass, the small neutrino mass may imply physics beyond the standard model. The mechanism to generate very small mass is called seesaw mechanism. And if neutrinos have very small mass, they change their flavor while propagating in the vacuum or in the matter, namely neutrino oscillations. And here I write the neutrino oscillation formula, assuming two-flavor vacuum oscillations. And from this, you can see, by the way, delta M square is neutrino mass square difference. And therefore, if the neutrino mass is smaller, then the neutrino oscillation length is getting longer. Therefore, by measuring the neutrino oscillation length, you know delta M square or neutrino mass. So it's clear that neutrino oscillation experiments are very important. Now, let's discuss the super Kamiokande experiment. It is a 50 kiloton water Cherenkov detector. It is indeed very large. It has about 40 meters in diameter and 40 meters high. And from the photo shown in the right, you see how big the detector is. And it is a very large international collaboration. Super Kamiokande has about 230 collaborators at present from 11 countries. This experiment has been taking data since 1996, and already in 1998, Super Kamiokande showed the first evidence for neutrino oscillations. And here I show the slide they used for demonstrating the evidence for neutrino oscillations. Well, this here in this slide, they showed the zenith angle dependence of electron neutrinos and muon neutrinos. And in particular, please look at the lower panel, which is the muon neutrino case. And cosine theta 1 means downgoing neutrinos, and -1 means upward-going neutrinos. They came from the other side of the Earth, traveling very long distances. And the data are shown by black circles. The expectations are shown by hatched histograms. And you see, for downgoing neutrinos, the data and the expectation agreed quite well. But for upward-going neutrinos, the data showed almost half of the data showed a very large deficit, almost half of the expectation. And in fact, they showed if we assume neutrino oscillations, the data can be fitted very well. In addition, Super Kamiokande had several other evidences for neutrino oscillations. And here in the right panel, I show the neutrino oscillation parameter space allowed regions from various measurements. And from these, Super Kamiokande concluded that the observed zenith angle dependent deficit and the other supporting data gave evidence for neutrino oscillations. So that was 1998. Well, I think that was indeed a very important discovery. And the world neutrino community was really excited with the discovery of neutrino oscillations. And since then, various atmospheric neutrinos and accelerator-based long baseline neutrino oscillation experiments have been studying neutrino oscillations in detail. And here in this slide, I show the experiments that contributed to our understanding of Newton-Neutral oscillations. So you see, there have been many experiments that contributed to our understanding of neutrino oscillations. In particular, in the last 25 years or so, the accelerator-based long baseline experiments have really contributed significantly. And let me tell you how much, how well we understand and how well we understood in the last 25 years. The first accelerator-based experiment that observed neutrino oscillation was the K2K experiment. They observed a deficit of muon neutrino events. In addition, they had some indication for the distortion of the energy spectrum, and the distortion was consistent with the neutrino oscillation expectation. The second experiment was the Minos experiment. They had the higher intensity neutrino beam, therefore they had much higher statistics, and therefore they had a very clear indication that the energy-dependent muon neutrino oscillation is completely consistent nu to nu tau oscillations. Then the current experiments are the T2K and NOVA experiments. And these experiments had a very good idea since they already knew the neutrino oscillation lengths rather well. Therefore, they tuned the neutrino energy so that the maximum oscillation effect should be observed. In fact, by looking at the T2K data, you see the observed muon neutrino event rate is much fewer than expected. Similar effect is also observed in NOVA, and these experiments are contributing significantly to understand the neutrino oscillation parameters. Of course, the previous experiments observed a deficit of muon neutrinos. But if the oscillation is mu to nu tau, we should be able to observe the appearance of tau neutrinos. And indeed, this was done. The OPERA experiment is a long baseline neutrino oscillation experiment, and they used the emulsion chambers, and with the use of emulsion, they observed the tau decay, and these taus are produced by nu tau interactions, and nu tau are created by nu to nu tau oscillations. So OPERA had a 5 sigma signal of the nu tau appearance. And similarly, Super Kamioka and Ice Cube observed the appearance of tau neutrinos. Now let me move on to the second oscillation channel, that is electron neutrino to muon neutrino plus tau neutrinos. As I said, in the 20th century, we had the solar neutrino problem. And in fact, this was a serious problem. And in 1985, there was a good idea proposed by Herb Chen. Well, he proposed to use heavy water. Well, let me read what he wrote in a paper. He said, a direct approach to resolve the solar neutrino problem would be to observe neutrinos by use of both neutral current and charge current reactions. Then the total neutrino flux and the electron neutrino flux would be separately determined to provide independent test of the neutrino oscillation hypothesis. And the standard solar model, a large heavy water detector sensitive to neutrinos from boron decay via the neutral current reaction, and the charged current reaction is suggested for this purpose. So he had this proposal. And then the snow experiment was constructed to observe solar neutrinos based on his idea. The snow experiment used 1,000 tons of heavy water. In the right, you see the photo of the snow detector during the construction. And in the middle, you see a very large vessel, which is a vessel to store 1,000 tons of heavy water. Now, indeed, the snow experiment was very successful. And I'd like to show you just one result from the snow experiment. Here, the snow data are plotted in the two-dimensional space. The horizontal axis is the nu-e flux, and the vertical axis is nu-mu to nu-tau flux. Now, charged current reaction can only constrain the electron neutrino flux, and the constraint is shown by the red band. In addition, the Snow experiment is sensitive to the neutral current reaction, and the constraint from the measurement of the neutral current reactions is shown by the blue band. In addition, Snow experiment is able to measure solar neutrinos by elastic scattering, which is mostly sensitive to electron neutrinos, but also with the reduced cross-section, they are able to measure the nu and nu-tau solar neutrinos. And the constraint from the electron scattering is shown by green band. Of course, super Kamiokande can measure the electrons, can measure the solar neutrinos by electron scattering, and the constraint from super K is shown by dark green. So you see these 3 or 4 different measurements intersect at a point, and the intersect point clearly indicates non-zero nu-mu plus nu-tau flux. And since the solar neutrinos, I should say, since the sun can only generate electron neutrinos, therefore the existence of nu-mu plus nu-tau flux clearly indicate that nu-e oscillated to nu-mu plus nu-tau. So this was the first evidence for solar neutrino oscillations. In addition, I'd like to mention another very important experiment. That was the Kamran experiment. Kamran is a 1 kiloton liquid scintillator detector constructed at the location of the Kamiokande experiment in Kamioka. And in early 20s, early this century, there were many nuclear power stations around Kamran at a distance of about 180 kilometers. So Kamran was able to observe these neutrinos, and therefore Kamran was basically a long baseline reactor neutrino oscillation experiment. And this is the data observed by Kamran. The horizontal axis is the energy of the neutrino events. And the dashed histogram shows the no oscillation expectation. And clearly, the Kamran data show the deficit of reactor anti-electron neutrinos. Furthermore, if they plot the data as a function of L by E, neutrino flight length over energy, then they were able to clearly show the oscillation pattern here in this figure. The vertical axis is the survival probability of the anti-electron neutrinos. So they observed this kind of the oscillation pattern. And indeed, this was in good agreement with the prediction assuming neutrino oscillations. So we were really convinced this is indeed neutrino oscillations. Now, I'd like to mention one more experiment. That is the Borexino experiment. Borexino was designed to measure sub-MeV solar neutrinos with extremely clean liquid scintillators. And here I show the data from Borexino. They showed the energy-dependent deficit of the solar neutrinos. And this energy-dependent deficit was completely consistent with the neutrino oscillation, with the neutrino oscillations in matter or MSW prediction. So we are very happy to see the data. The data were consistent with the MSW prediction. Furthermore, we are very happy that Borexino was able to observe the CNO solar neutrinos. So I think basically we understood the solar neutrinos very well. Okay, so far I discussed nu mu to nu tau oscillations and nu e to nu mu plus nu tau oscillations. But since there are three flavors, therefore there should be the third oscillation channel. In fact, after the confirmation of the solar neutrino oscillations, the community's main interest was the discovery of the third oscillation channel. Indeed, here I list the experiments that was constructed for the observation of the third oscillation channels. There are two ways. One is to use the accelerator neutrino beam, and they would like to observe nu mu to nu e oscillation. Another method is to observe the reactor neutrinos at relatively short distances of 1 to 2 kilometers. And in fact, these experiments observed evidence for third oscillation channel. Here, I show the data from these experiments around 2011 to 2012. Already at that time, the data from these experiments were strong enough, and therefore, at that point, we concluded that the basic structure for three-flavor oscillations had been understood. Well, of course, this was the data more than 10 years ago. Since then, these experiments have been improving their experiments significantly. Therefore, at present, our understanding is much better. Anyway, I'd like to summarize the experiments that contributed to our understanding of neutrino oscillations. There are several atmospheric neutrino oscillation experiments, solar neutrino oscillation experiments, accelerator-based neutrino oscillation experiments, and three-flavor neutrino oscillation experiments. They use either the accelerator neutrino beam or the reactor neutrinos. Now, these experiments have been indeed contributed significantly to our understanding of neutrino oscillation parameters. And here I summarize, well, taken from this reference, here I summarize the present status of the understanding of neutrino oscillation parameters. Well, there are three mixing angles, theta 1, 2, theta 2, 3, and theta 1, 3, and two delta m squares, neutrino mass square difference, delta m 21 square and delta m 31 square. Unfortunately, at present, we do not know if delta m 31 square is negative or positive. That means we do not know if the nu3 mass state is the heaviest or the lightest. And therefore, in these graphs, there are two curves. One assumes normal mass ordering, the other assumes inverted mass ordering. Anyway, through the studies of these neutrino oscillations, basically, we understood that neutrino mass is very small, probably more than 10 orders of magnitude smaller than the corresponding mass of quarks and charged leptons. So neutrino mass is very small. Furthermore, we understood that neutrino mixing angles are large compared with the corresponding quark mixing angles. By the way, I'd like to remind you, now we understood the neutrino parameters rather well. Here, I show the 1 sigma uncertainty for these parameters, assuming normal mass ordering. You see the accuracy is between 1 and 3%. So our understanding is rather precise. Okay, now I'd like to move on to the future prospect. As I said, now we understood neutrino oscillation parameters rather well. But there are still unknowns in neutrinos. Here I summarize the unknowns in neutrinos. First of all, we do not know the neutrino mass ordering, as I explained in the previous slide. We do not know the nu3 mass state is the heaviest or the lightest. And since neutrino oscillation experiments can only tell the neutrino mass square difference, we do not know, we cannot measure the absolute neutrino mass. Furthermore, we do not know if CP is violated in neutrino oscillation parameter, neutrino oscillations. Namely, we do not know if the oscillation probability is same as the anti-neutrino oscillation parameters, anti-neutrino oscillation probability. Furthermore, we do not know if there's a structure beyond the minimal three-flavor framework. And finally, we do not know if neutrinos are Majorana particles. Well, we have to understood these, we have to answer these questions. But from now on, I'd like to concentrate on the two problems, that is neutrino mass ordering and CP violation. Okay, neutrino mass ordering. Well, as I said, at present, we do not know the neutrino mass ordering. Well, to be honest, the present data slightly favor normal mass ordering. Delta chi-square is 6 point some. Therefore, normal mass ordering is favored. But the statistical evidence is not strong enough. Furthermore, I'd like to remind you that we naively expect that the neutrino mass ordering should be normal. However, there have been many unexpected surprises in neutrino oscillations, such as large mixing angles. And therefore, I think we should experimentally test the neutrino mass ordering. In fact, there are several experiments that could measure the neutrino mass ordering. For example, Juno, Dune, INO, Hyperkamiokande, Ice Cube, KM3net, Orca, and so on. And probably Juno will be the first to tell us the mass ordering at better than 3 sigma. And Dune will give very high confidence results. And of course, other experiments will also contribute significantly. But anyway, now I'd like to discuss the Juno and Dune experiments. Juno is a very large liquid scintillator detector, which has 20,000 tons, and it will detect anti-electron neutrinos from nuclear power stations at a distance of 52.5 kilometers away. And the detector will be ready in this year. And in the left bottom panel, I show the expectations for the energy spectrum measured by Juno for inverted and normal mass ordering. As you see, depending on the mass ordering, the spectrum shape should be different. Therefore, Juno experiment is going to measure this spectrum difference. In fact, this is not an easy experiment. Juno has to be very careful about evaluating the systematic errors. But anyway, after, say, 6 or so years, Juno should be able to tell us the mass ordering at 3 sigma level. Another experiment should be Dune. Dune is a very long baseline neutrino oscillation experiment with very large liquid argon detectors. The baseline length is 1,300 kilometers. And because of this very long baseline, the matter effect is very large. Therefore, in a sense, Dune is an ideal detector, ideal experiment to observe the mass ordering. In fact, here they plotted the expected number of electron neutrino events versus the anti-electron neutrino events. And depending on the mass ordering and CP violation phase, they should be able to observe these many neutrinos. And you see the statistical errors should be very small. And therefore, after some exposures, in this graph, 336 kiloton megawatt years or 624 kiloton megawatt years, they should be able to tell us the mass ordering very precisely, much better than 5 sigma. Finally, I'd like to discuss future prospect on CP violation. Well, First of all, we'd like to confirm that CP is violated in the neutrino sector, and CP violation in the neutrino sector might be the key to understand the baryon asymmetry of the universe. This is very important. So we really want to observe CP violation. Let me look at the present data. There are two experiments that could be sensitive to the CP violation. One is the NOVA experiment, another is the T2K experiment. And in both experiments, the data are plotted in a two-dimensional plane. The horizontal axis is the neutrino events. The vertical axis is the anti-neutrino events. And depending on the mass ordering and CP violation phase, and actually theta 2 3-octant, data could be somewhere. And by measuring the neutrino appearance events and anti-neutrino appearance events, they'd like to get the information on the CP violation. And the NOVA data are shown here, and the T2K data are shown here. Well, first of all, the NOVA data and T2K data may not be completely consistent. Therefore, I think we should have the next generation experiments that are much sensitive to the CP phase, CP violation. And indeed, there are two experiments going on. One is the Dune experiment in United States, another is the hyperkamiokande experiment in Japan. Both uses the neutrino beam produced by accelerators, and they would like to observe the electroneutrino appearance and anti-electroneutrino appearance at the far detectors. And in fact, these experiments have very high sensitivity to the CP violation. Well, depending on the true CP violation phase, they should be able to observe the CP violation at more than 5 sigma confidence level. So we really want to see the data from these experiments. And now, before finishing, I'd like to mention the hyperkamiokande experiment. Well, hyperkamiokande is the third generation water Cherenkov detector. And you see the water Cherenkov detector have been contributed significantly to neutrino physics and neutrino oscillation physics. Therefore, I think it's natural to expect a significant contribution by the third generation experiment, Hyper-K. In fact, hyperkamiokande is under construction. The construction started in 2020. At present, the top part of the main cavity has been excavated. And from now on, the excavation to the lower part of the main cavity will be starting. Well, by the way, here I show you a photo of the hyperkamiokande construction. In October last year, the top part of the hyperkamiokande main cavity was excavated, and this photo was taken at that time. So the construction is going on schedule, and the experiment will start in 2027. And of course, this is an extremely large water Cherenkov detector, and we expect many important research topics in neutrino physics and astrophysics. By the way, hyperkamiokande is a very large international collaboration. It has about 600 members from 22 countries. And in fact, we are hoping a very significant contribution from the Indian neutrino research community to hyperkamiokande. Okay, let me summarize. Neutrinos have been playing very important roles in understanding the laws of nature, in particular laws at the smallest scales. Recent discovery and studies of neutrino oscillations and the small neutrino mass will be very important to understand the physics beyond the standard model of particle physics. Neutrinos with small mass might also be the key to understand the big questions in the largest scale, namely the universe. We'd like to understand why only matter particles exist at the present-day universe. So neutrinos are likely to continue playing very important roles in understanding the nature in the smallest and the largest scales. Okay, that's all from me. Thank you very much.
Thank you, Kajita-san, for your nice talk and for telling us about all these oscillation experiments. So now the floor is open for questions. So I would like to request, if you have any questions, please raise hand and we'd be happy to take them one by one. And especially I encourage students. I can see there are so many students. I understand that, it's difficult for them to understand, what we have been discussing. But if they have any question related to neutrinos, any general question, we would be happy to take them. So please, come forward and ask if you have any questions or comments. Yes, Anil, you have any comment or question?
Yeah, first of all, thank you for this wonderful talk. So I'm Anil Kumar. I'm a postdoc from IceCube group. I have a question regarding one plot. Like for Hyper K, you showed that it has CP violation sensitivity good. So I was curious that compared to Super K, what is extra in their Hyper K which brings this good sensitivity for CP violation?
Okay, thank you very much. Well, of course, the sensitivity is essentially determined by the statistics. And compared with the present T2K experiment, the beam power will be upgraded at the JPAC site. And also, of course, Hyper K is much larger than Super K. And therefore, approximately, we'll have a factor of 20 improvement in statistics. And that statistics is the key to have this high sensitivity in CP violation.
Thank you.
Yes, Siddharth. You can open your video if you want and introduce
Oh,
yourself.
okay, sir. My name is Siddharth Bandapade. I'm from ISER, Kolkata, in India. So great talk. My question was regarding like the neutrinos that we measure from, say, astrophysical events. Like we have measured neutrinos from, say, a supernova, like far away in the universe. Like, can we also measure with present technology neutrinos from, say, neutron stars and talk about oscillation in those scenarios? Like, is it possible with present detector technology?
Well, excuse me, I'm not completely, and I'm not sure if I completely understand your question. So are you asking if we can get information on neutrino oscillations by measuring the astrophysical neutrinos?
Yes, like I'm saying that we have measured like solar neutrinos and also neutrinos from supernovae. So can we like presently detect neutrinos from neutron stars or like more distant objects as well? And if so, can we like talk about oscillation there, like neutrino oscillations in that scenario?
Okay, thank you very much. Well, okay, it's a difficult question. Well, first of all, from neutron stars, I naively do not expect any significant neutrino flux. But if binary neutron star merge, then at that moment, there should be a significant neutrino flux. However, unfortunately, the event rate of the binary neutron star merger is very low. I don't remember the event rate, but very, very low. Therefore, it may not be realistic to think about the measurement of the neutrinos from the binary neutron star mergers. Also, I have no idea if these observations could contribute to the understanding of neutrino oscillations. I'm sorry, I don't know.
Good morning, sir. Sir, I have a question. Sir, how neutrino mass helps to understand the physics?
So you are from the Cohen International School. Yes, can you repeat your question?
Sir, how neutrino mass helps to understand the physics?
How neutrino mass? Can you be louder?
How neutrino mass helps to understand the physics?
Understand the physics.
Yes, sir.
Okay. Well, okay, thank you for the question. Well, I said that neutrino mass is very, very small. Maybe more than 10 orders of magnitude smaller compared with the mass of quarks and charged leptons. Now, in the standard model, mass of quarks and charged leptons are believed to be, are generated by the Higgs mechanism. However, since the neutrino mass is extremely small, we believe that we need other mechanism to generate the very small neutrino mass. And this mechanism must be beyond the standard model of particle physics. And therefore, we are excited with the very small neutrino mass.
You have any further question from school, from the students? I'm asking the students from the school, like if you have any question, feel free. This can be any general question related to neutrinos.
I have one question.
Yes.
Okay. May I go first?
Yeah, Avnish, just wait, let the students finish and then we take up your question.
Yes, sir. Sure.
Okay.
Good morning, sir. So my question is, if neutrino oscillates and they have mass, what will happen if they collide? And what is the charge neutrino?
Okay, Kajita-san, did you hear the question that, I think they said that if what would happen if neutrinos will collide and what would happen with the charge of the neutrinos? Is that correct? I'm asking the student, do we hear you well? This is your question?
Sir, my question is, if neutrino oscillates and they have mass, what will happen if they collide?
Okay.
And another question is, what is the charge neutrino?
Okay.
Well, thank you. It's a very interesting question. What will happen if neutrinos collide? Well, first of all, it will be very difficult to observe neutrinos to collide. But anyway, if they collide, neutrino could change to other particles. Well, certainly, based on the standard model of particle physics, we can calculate what will happen. Anyway, this is an interesting question. Thank you very much. And what was the second question?
I think the second question was something related to the charge of the neutrinos. So
yes, thank you. Yeah.
Mention that it's neutral. So maybe I think
yeah, thank you very much. Well, okay. I think the neutrino charge is exactly 0. So far we have no evidence that neutrinos have charge. So I believe neutrinos have 0 charge.
In fact, for the students, I would like to add that what Kajita-san told us, that neutrinos have mass, but remember, they don't have charge. In fact, that was one of the reasons that it took us almost 50 years, 40, 50 years to have these experiments and detect neutrinos by significant amount, because they are neutral particle. So you can't use electric field, magnetic field to observe these neutrinos because they are neutral particles. So this is a challenge for all of you. This has been a challenge for all of us, how to detect neutrinos. And there comes the contribution of Kajita-san. So for last 4 decades, he showed us with many, many experiments in Japan that we can detect neutrinos, but it is very tough. But the toughness comes because they are neutral. One of the reasons. Yes, Avnish, please go ahead.
Thank you, Professor Kajita, for your wonderful and very refreshing talk about this neutrino. And I have one question regarding, these neutrinos make out of the previously think of the elusive particles, which now we have been able to understand. And there is one another member particle, means proposed one, like this tachyonic states are residing, which we have not till so far found. And neutrino experiments present us one opportunity to look at means long baseline experiments where we can propagate a neutrino, as we suppose that neutrino is a tachyonic state, and we try to detect at some location the incoming time and send a photon and compare those times. There was some difference around the 16 nanosecond. So I'm curious that claim has been withdrawn in 2012 past, but what is the status now? Means, are we exploring that dimension till now, or means it will be better if you talk about this?
Okay, thank you. Okay, well, I think you are talking about the a claim about 10 years ago that neutrinos travel faster than light by an experiment. Yeah. As far as I understand, there was some mistake in the experiment. So at present, there is no evidence for tachyonic nature in neutrinos.
So I'm more curious about, is there any way in upcoming neutrino, this kind of state we can try to explore more? Means, is there any avenue to search those things?
Okay, thank you. Yes. Well, suppose a supernova explodes in our Milky Way galaxy, and of course, we should be able to observe many neutrinos, a neutrino burst. But in addition, nowadays, we should be able to observe gravitational waves from the same event. And by comparing the arrival timing of these two neutrinos and gravitational waves, we should be able to tell the relative speed of these two messengers.
That's very wonderful information for me. Thank you, sir.
Can see another hand over there. Can you open your video? There is a hand over there.
Yes, sir.
Yeah.
Thank you, sir. Thank you, sir, for this great talk. I'm Haska. I'm a MSc student at IIT Bhubaneswar. So my question is that till now we have discovered only 3 flavors of neutrino, like the mu neutrino, tau neutrino, and electron neutrino. So is there any possibilities in the future that we might have some another flavors of neutrino? And if not, then why?
Yeah, thank you very much for this question. In fact, today I didn't discuss anything about this topic, but on the other hand, there are some data which may not be convincing enough, but these data indicate that there could be the fourth neutrino state. But well, at present, we are not convinced yet. Therefore, the community is still working if there is indeed a fourth neutrino mass state. Well, so there is a possibility, but we do not know yet.
And sir, if we might discover that fourth kind of flavor, then is it possible to detect that with the technologies that we have now, or we have to invent some another kind of technology for that?
Thank you. Thank you. The point is that if there is a fourth neutrino type, then there should be neutrino oscillations between normal neutrinos and the fourth neutrinos. And therefore, even if the fourth neutrino is generated, they should oscillate to, a part of them should oscillate to normal neutrinos. Therefore, we should be able to observe these neutrinos. And by analyzing the data, we should get information on the fourth state. That is the idea.
Thank you, sir. Thank you so much.
Kajita-san, we were live streaming your talk over YouTube, so there is a question over there. Can I take it?
Okay.
Yeah. So the question is, when should we say that something has very small mass? Is there any chance in future that we can have particles which have more smaller mass than neutrinos?
Okay, well, okay. This is a very important question.
Right.
I don't know the exact answer, but well, our universe began with Big Bang, and Big Bang universe, many neutrinos were created, and in fact, by the data of the cosmology, we know that neutrino mass state is approximately 3. Therefore, the unknown particle, still unknown particle, is something like neutrinos. We have a constraint by cosmology. Therefore, if you think about these yet another very small mass particle, you have to seriously check if your proposal is consistent with cosmology.
Thank you, Kajita-san. Are there any questions? Yeah, I see one more hand. Go ahead, Apia.
Hello. Yeah. Oh, sorry.
Yes, go ahead.
Hello, sir. I am from Kohit International School. I have a question. Sir,
So,
can you please...
we can't hear you. Can you talk a little bit louder?
Yes, sir. Sir, can you please explain about relationship of neutrino with space?
I'm sorry, we can't hear you clearly. Can you be a little bit louder? Yes, I appreciate your question, but we can't hear you. Can you come closer to the microphone and ask again your question?
Yes, sir. Can you please explain about relationship of neutrino with space?
Relationship between neutrino and what?
With space.
It's spin or what?
Space.
Space.
Universe.
Oh, so universe. Okay, good. So let me repeat the question. The young student is asking whether we can have some light on the relationship between neutrinos and our universe. Very good question.
Very good question. Well, in fact, I think neutrinos are playing very important role in the history of the universe. Well, for example, because of the very small neutrino mass, the neutrino's contribution to the formation of the structure of the present day universe can be, well, difficult to say. Well, anyway, short question to your question, a short answer to your question is, yes, neutrinos play a very important role in the universe. There are various ways that neutrinos contribute to the universe.
In fact, just I would like to add what we learned from Kajita-san, from his thesis, from his talks. Like he mentioned today about solar neutrinos. So we get solar neutrinos when there are fusion processes inside the sun. So just for you, for the student, I'm just telling that if these processes will not happen, we will not see sun shining. So you understand that, if sun will not shine, what would happen? Can we imagine our universe if the sun will not shine? And the reason that sun shines in light and also in neutrinos. So this is one of the biggest motivation that we should learn about neutrinos, because these neutrinos are responsible for shining of the sun. Just one example.
Thank you very much. Wonderful comment. Thank you very much.
Yeah, just I wanted to share, Yeah. I can see a hand by Pasha. Yeah. Yeah. Is there any more question?
I'm also a student of Bohemian International School. Yes,
sir. Sorry, we can't hear you properly. Can you repeat?
Sir, I am also the Bohemian International School. I have a question.
Yes.
Can neutrino be used in any other way for human purpose? Like we use solar energy to generate electricity.
So Kajita-san, may I repeat? The young guy is asking that can we use neutrinos for mankind? Like, we can use solar energies definitely now with solar panels. We reserve solar energies and we use in our day-to-day life. So he is asking how neutrinos can be useful for the mankind.
Well, thank you. This is a difficult question. To be honest, I have no idea if we can use neutrinos in our daily life in the future. But of course, you are young, you may have great idea. So maybe in the future, neutrinos could be very important in our daily life. Well, I don't know.
Maybe this is a question for you. You start thinking about that. Okay. Okay. Are there any questions? I don't see any further hand. Anil, are there any questions over YouTube?
Hello?
No, yeah.
Can you hear me? Yeah.
Yes.
Okay, so I'm a student of University of Hyderabad. So hello, thank you, Kajita sir, for your wonderful talk. So I have a question. I heard that in presence of mass, the space-time is changed. So as neutrinos, we know that the neutrinos are massive particle. Obviously, it's a very small mass, but can't we use the space-time gravity on the neutrino oscillation calculation? And if it is so, then what will happen in the neutrino oscillation calculation?
Oh, thank you very much. I think this question is too difficult for me. So I don't know. I'm sorry.
Okay, thank you.
So Amol, you wanna comment something? Or do you have any questions? You are muted, Amol.
No, so regarding this earlier question about uses of neutrino, I mean, I know the Kajita-san is very down-to-earth person and he doesn't want to speculate too far in future. Maybe I'll get his comments on some of the futuristic things that have been speculated about uses of neutrinos. So one was about neutrino communication. Because they go through the earth, they can reach faster on the other side. And the second was about things like oil exploration by passing neutrino beams. Do you have any comments about the feasibility of these ideas in near future?
For near future.
Well, okay, far
certainly.
Far future.
Yeah, certainly. There could be possibilities, but well, yeah, certainly possibility. However, if we think about the efficiency, well, well, certainly the efficiency should be very low. Therefore, there should be always problems related to the energy to generate neutrinos, and therefore, in the commercial world, it may not be materialized.
But as scientists, we are allowed to speculate.
Yeah.
I think we had a lot of questions, and especially the questions from the students were very interesting and innovative, I believe. They were very fresh. So I would like to thank the students, for listening the talk. And let's see, I don't see any further hands. So Anil, you want to take a picture with Kajita-san or some of you? So then we can do that. Maybe you can just switch on your videos if you are comfortable and have this opportunity to take a snap with Kajita-san. It's a memory. So if all of you can kindly switch on your video, and I request Anil or Masum if you guys can take a picture. No. Great. So I'm seeing the faces are coming up. Yep. Yeah. So kindly, if you can open your videos and we just stay for 30 seconds or a minute. Yep. Yeah. So maybe Anil or any of you just take a picture and then let us know when you are done. So you are done with that?
Yeah, I'm done. I took, yes, future pictures.
Thank you, Anil. Thank you. So Kajita-san, I don't have any words. I don't think that, only saying thank you is enough. It will be a memorable moment for, even for me in my life, having, this question answer session with you. And, I know how busy you are, but, you accepted our request and you came and gave this talk. And I believe that your life, your journey in neutrinos will keep on, inspiring us. And I wish you good luck for this, HYPERC experiment, which we are all waiting. In fact, next month, Juno is going to start. So we are very much excited. And the success of Kamiokande, Super Kamiokande, K2K, T2K, and now Hyper Kamiokande will definitely inspire us, a country like India, to invest more on neutrinos and do experiments. And thank you for all your support, all your time. And we hope that we will be able to welcome you in IOP in person in near future. And you will consider this. So thank you, Kajita-san, for your time and for this talk and for telling us, what is happening. So thanks a lot.
Thank you very much.
Thanks a lot.
It was indeed my pleasure to give this talk. Thank you very much.
Yeah,
And congratulations for the Golden Jubilee via Institute.
thank you, Kajita-san. Have a nice evening.
Thank you.